that's in the CMS event display. You can see many overlapping events, and also signatures in our calorimeters. There you see the red muons bending in our magnetic field, and absolutely
and
fantastic.
And this was just 15 minutes after the switch on.
No, we
this is an incredible machine.
So
I've asked Atlas, I have to ask you the same question. What's the program for CMS this year?
Also exploiting the maximum potential of CMS, so we have to keep up with the increased number of particles that the LHC is going to give us per interaction. So this is creeping up every year, and now we have to reconstruct 40 to 50, 60 overlapping events. And so for CMS, we have to exploit our new pixel detector, image, 3D image, the location of all the individual vertices. And then, like Atlas, we're trying to look for new physics, and we're trying to understand in detail the difference between the theory predictions and the measurements in our detector to try and explore very small deviations, which could be hints of new physics.
Fantastic. And also Anne Dabrowski from CMS is staying around this table, is ready to take your questions. I encourage you to post them under the Facebook live video. So now time to tour around the ring again. We continue going around and go to interaction point number 2. You can see it on the left bottom part of the screen. There's Alice. The Alice detector stands on French territory in Saint-Genis. And we have here for Alice Despina. I cannot pronounce your family name, I'm sorry. Can you say that? Okay, Despina is from Greece, but is one of the physicists of the Alice collaboration. So Alice specializes in quark-gluon plasma studies, a stage of the universe when, very early universe, primordial universe, when the quark and gluons were deconfined, as you say. And usually you do that when the LHC runs lead-ion collisions, not proton-proton collisions.
Exactly.
And we learned from Jamie, he told me, this year, no lead-ion collisions. Exactly. You will have proton-proton collisions. So tell us about Alice. What can Alice do with proton-proton collisions?
Well, Alice, of course, doesn't sit around when there are no lead collisions. We record data also with proton-proton collisions, and we use them in two ways. One way is as a reference for the lead-lead collisions, to do a comparison, and there observing differences in the two systems, we deduce that this exotic strand of matter, the quark-gluon plasma, is formed in the case of heavy ion collisions. But also we do proton physics in itself with the possibilities that our detector offers us. And actually, lately, we published a paper which appeared in Nature last month, which is exactly the observation of something very interesting in proton-proton collisions. And this is that the observation that strangeness enhancement, which was one of the first signatures of this quark-gluon plasma, first seen 30 years ago, and which was associated only with lead collisions, we saw this phenomenon also in proton collisions at 70 eV. This is data from the first run of LHC. But in the particular case, when the multiplicity, which means the number of particles, the total number of charged particles produced in the collision, is very high. So this is certainly something intriguing, which makes us have an extra interest in the proton-proton system. So we hope to study more with the new data that come this year. And in addition, we have requested for this year, at the end of the run, to have a dedicated run at lower energy, so that we can compare with data from lead-lead, which correspond to the same energy center of mass.
I see. So for sure you make the most of this proton run just started right now and for the rest of the year. Thank you, Despina. You stay with us. There will be a question for Alice, I'm sure. Let's now go to the last but not least, of course, interaction point around the LHC ring, LHC point 8, which is very close to the Geneva airport, but still in France, in French territory, where the LHCb experiment is situated. We have here for LHCb Barbara Storaci.
Hi.
Welcome, Barbara. So, Barbara, also for LHCb, I guess yesterday was lots of excitement around the first collisions.
Yes, it's always a great emotion. I can tell you, since I'm a bit young, but I had the lucky fortune to be there every single times for all the collision,
restarts, yes.
the restarts, also the very first one. And along the years, I thought that the emotion will go down, but in fact, no. Every time it's just a great emotion. It's just you are there waiting, and finally you see your detector alive again, your collision coming, and you know that you are ready for a new start of discovery, so of data that
That's
can
amazing.
really bring you.
We have one of your first
Yeah.
events here. Can you comment on it?
Yes, so again, you can see that also in our case, a few minutes after the first collision, we produced this nice event display. You can notice that we are slightly different from the other experiment, in particular Atlas and CMS, that they have this cylindrical, or as I like to call it, onion shape. We are more like books in the shells.
Yes.
And you can see these lines are the trajectory of our particles, and one of the most important things is to try to reconstruct this trajectory and understand which particle produced them. And you can see really that all our detectors are alive and give a nice signature. So we are ready to start analyzing data and try to discover something.
What are your challenges?
Yeah, so these years are very exciting for us. So more data will come, and this will be very important, as my colleagues from the other experiment already said, because we saw in the previous year some potential discrepancy with the standard model, that we don't have enough statistics yet, so we didn't collect enough data to know if they are real sign of new physics or just, normal fluctuations. So now this extra data will be essential to see if they are still there, and we are at the start of a new era. So really, these are the years where you want to be
I have a little feeling
here.
that your preference is for discrepancy confirmation.
Absolutely.
So now it's time for questions. There are already coming quite a lot of questions. I have the first one for Atlas from Paul Johnson. Thank you, Paul, for this question. What energy is theoretically required to find evidence of super partners? And at what point do you give up on supersymmetry? Alexander, big chunk for you.
That is a big chunk for me, exactly. So let's see. So the theory you're alluding to is probably SUSY. And of course, the theory allows a wide range of masses for superpartners. Now, and the experiment, Atlas experiment at the LHC, is very well within that range that is theoretically allowed. So maybe the most prominent is the top superpartner, which should be one of the lower lying fruits, which he could detect if SUSY exists. And with the data set we have collected so far, the limit is about at a TeV or so, where we can say up to a TeV a stop does not exist, but maybe above. Now, you might argue we have 13 TeV at the LHC, so it's only 1 TeV. The reason is that not at every collision, not all that energy can be transferred into a mass of a new object. So there's a certain statistical process. So we hope with this more data we get now that we can either extend our knowledge to say it must be heavier than X, or, which is certainly the more exciting variant, is we discover it. So that
would be really exciting. There's now a question for CMS from Dharanesh Sonu. Dark matter still remains a mystery. Mm-hmm. Does CERN think they can understand completely what dark matter is? Mm-hmm. Sure. You need a microphone. Yeah. Yes.
Well, certainly one of our searches is for dark matter, and how we look for it is we look in our event displays for missing energy. And if we can't explain that missing energy with, for example, a standard model particle like a neutrino, then we have to scratch our heads and try and understand what it is. It could be dark matter, or another thing is we look for processes that, So the question, can CERN contribute to the search for
search.
Yeah, I would say absolutely. It's one of our top priorities, and the Collider experiments are well suited to looking for this missing energy. And of course, we also keep our heads onto the rest of the international community dark matter is also searched for in other underground experiments.
In
astrophysics, neutrino experiments, and so on.
Right.
So
You're all working together, and any hint from each of you is
Exactly.
a step forward for all.
Exactly.
That's amazing. Okay, there's a question from Frederick Joseph Whittaker. Is live data from many of the detectors ever made available to the public or citizen scientists? Anyone wants to take this question? I know there is a program of participating in the data analysis from BOINC. I don't know, maybe you want to take that?
Yeah, I'm not sure. Maybe then we can have some help. So not totally sure about exactly what are the politics about that. But yes, I'm aware of this BOINC, or how it's called exactly, program in which you use the CPU from people around the world.
This computer.
Exactly,
Yes.
to contribute in the CPU needed for analyze the data. Then there is also some, I think there are some activities for students, for example, that you give some old data and you simplify. This is an kind of outreach, but not only activities to get the high school students to have a feeling and start to
learn,
learn, and also maybe they become a physicist. Then there's also some program, I don't know if somebody here has more knowledge than me about the open data.
yes.
So that's also quite an interesting thing. So it's a discussion that is, at least from what I know, ongoing in the community.
That's great. I have a question for you, Despina. Maybe it's also a question for Jamie. I don't know. You decide, why are there no lead collision this year at the LHC?
I don't really know, but I imagine that there was a big request from the other experiments to collect more proton statistics, and therefore the lead program was postponed for 2018.
Who decided that?
Yeah, I mean, I guess I'm partly responsible for this. The thing is, of course, we have different requests from the different experiments, and this year the physics data started a bit later than normal because CMS did this big intervention in their detector and replaced the pixel detector, which was a big intervention. And this means there's less days for physics data. So it was decided amongst the very big bosses at CERN that for this reason, this year we would just concentrate on proton-proton collisions. And next year we have the last month, so in 2018 we have the last month scheduled for lead-lead collisions, which will be for ALICE but also for the other experiments.
Great. Just a relaxing question for everyone. What is your fundamental particle? Let's start with you, Despina. What is your preferred fundamental particle? From YouTube, Tyler Codell.
My personal preferred particle?
Yes.
The electron.
The electron. You're a free electron. And you, Anna?
I have to agree. I'm an electron too, yeah.
That's great. Jamie?
Well, I'll go for the Higgs boson. Since I was around working on the ATLAS experiment at the time when this was discovered, and I was sort of involved in this, so this was a very exciting time.
Oh, this is unforgettable, of course.
It's the easy one to go for, I'm afraid.
Alexander?
Yeah, I'm afraid I'm boring also.